program is an interdisciplinary forum for sharing of information knowledge, and we have a great opportunity and pleasure to host scholars of global importance who have shaped fields over a period of time. And this program is one of the aims as part of the University of Hyderabad, or the center I teach over globalization and other kind of motives, is to have dialogues irrespective of disciplinary boundaries. So having said that, today we are absolutely fortunate to have Professor Gerry Altmann, and I'm slightly intimidated to introduce Gerry. Although Gerry would be funny about himself, please watch out his website. The tidbits he writes about his CV. Let me tell you that Gerry's name is synonymous with contemporary psycholinguistics, or maybe you can say psycholinguistics after 60s or 70s. That's how I visualize it. This is an enormous influence in many fields, in psycholinguistics, mind-brain sciences now. So Gerry taught for many years at the University of York and has shaped careers of many people, among them one of my long-term friend and collaborator, Paul Kuttig. And I think the influence on me on language-visual interaction when I took it up must have been there, and I still continue with that. And then Gerry has moved more recently to University of Connecticut, where he directs the Institute for Brain and Cognitive Sciences. It's about 2015, I think he moved there. And his interests have changed over a period of time. Initially, he made very groundbreaking contribution to language sentence processing. And one of his models are still, I teach and others teach. The influence of context on sentence processing. And more recently, or since many years, I think he has been deeply interested in visual event representation and the way language influences and gets influenced in return. And he has used eye tracking, many other methods over a period of time. Among other things, Gerry has been a long-time editor of the prestigious journal Cognition. And I think it shaped the journal in many, many ways. And he's one of the books, he has written and edited many books. One of the books, The Ash and the Barrel, won probably the British Psychological Academy's award. And I didn't know that your portrait hangs in National Portrait Gallery in London. I can imagine it. Interesting. So today he would be talking on event representation and involving language and the give and take between them. And I think he will be using parts of pre-recorded talks and visuals, and then the audience would have a chance to ask questions at the end. However it goes, we are pretty open about that. It's not a rigid platform. So again, I would say that I'm very happy to have you on this program, and I'm quite sure that those who are watching and who will be watching later on the YouTube channel, recorded YouTube, when we put it on the University of Hyderabad website, which has a pretty large, massive subscribers. Whatever you said today would influence a lot of people who are watching, students here who want to take up research in both language and related fields. So with these words, I welcome you again, and now the floor is yours.
Well, thank you very much for that introduction. Let me just say what an incredible honor it is to be invited to speak as a part of this series. And the Center for Neural and Cognitive Sciences is just a fantastic center. It's a beacon in India, and it's just wonderful to see the work that comes out of there, and the work that you, Ramesh, do and lead, and all your colleagues there. It really is an inspiration for many, many people. So I'm very honored. I looked at the other speakers you've had, and clearly something went wrong, and you've gone down to the second and third tier of speaker.
No judgment here. No.
So no, it really is a fantastic honor. I'm trying something a little bit different with this talk, because I've pre-recorded the talk in 3 sections. And I've actually found that this is a really interesting format to use. So after each section, I'll pause and invite questions on that section, and I'll explain that at the beginning of the talk. I'm going to be talking about today some work that I've been doing over the past decade or so with a number of people, two students of mine at UConn, Zach Ekvies and Janina Pristauka, Forrest Davis, who's a computational wizard at Cornell, and then Nick Hindi, Sarah Solomon, and Sharon Thompson-Schill, with whom I first embarked on human neuroimaging. We're all interested in event structure and specifically how it is that we encode the content of events. And I'm going to divide the talk into three parts. First, I'll start with some theory, then I'll talk about some relevant behavioral work, including some neuroimaging, and then I'll end with a computational perspective using recurrent neural networks to model some of the phenomena I'll be talking about. At the end of each of these three sections, I'll be stopping and inviting questions. So we all have a pretty good idea of what we mean by an event, but I want to be very clear about what I shall be meaning by that term. And for me, an event happens if something changes state over time. So here's an example of a typical event. We have our chef, Gordon Ramsay, chopping an onion, and the onion is changing state from intact to chopped. And the question we have is, how do we encode the representation of such events? And how do we do that whether we're observing an event, as we did when watching this little movie, or when we read or hear a description of such an event, such as this one at the bottom here, the chef chopped the onion. Now, if we had tracked the entire event, we would have noticed that the onion started off intact, then it was peeled, then perhaps it was halved, and then one half was chopped. So we need to, in order to encode the event, we need to track this particular instance of an onion across time. But we have to do more than that, because in this case, for example, we have to somehow encode that the two onions that are encircled at the top here, the intact one and the peeled one, are in fact different instances of onions than the one that was actually chopped. So we have to distinguish between different instances and track individual instances. So why care about representing this kind of change? Why care about tracking tokens and distinguishing between different instances of things? Well, for me, cognition is about the ability to internally represent the external world. So that means the ability to encode types of things, onions, oranges, chairs, but also to instantiate the actual things, the tokens that I actually encounter in the external world. It's an ability, by the way, shared with slime molds, that is, encoding, representing, anticipating, causing, and acting on change. And I can come back to that in questions if you're curious about slime mold. Okay, let me start then with the underlying theory that we're adopting for this journey. So I mentioned when we were viewing this that there was onions, there's a chef, the onion is changing state. There's a lot going on. So we can think of events as ensembles of representations, some collection of that whole lot of stuff that is happening. But what are these ensembles of representations? What are they representations of? Well, individuated objects, that is tokens, their histories, and I shall come back to that in a moment, and the relationship between one token's history and another token's history. Now, by history, I really just mean that tracking of the object across time as it changes state. And in this little cartoon, I'm depicting that in the following way. I'm assuming that I have a representation of an object in some semantic space that represents its features across time. And that object undergoes some change in those features through time, and we can think of that as a trajectory. Of course, a trajectory doesn't finish with the chopped onion. Other stuff happens later. Now, in the case of the movie that we watched, there's also a knife that comes in and intersects both figuratively and literally with the onion. And there is also the chef, Gordon, who picks up the knife and then attacks the onion, and then presumably puts the knife down and goes off on his the rest of his life. So this is what we mean by an event being a collection of intersecting object histories. Now, you don't have to have more than one object for an event to take place. It could just change state without any such interactions. But there could be such interactions, and this is what they would look like in the state space. Now, importantly, we're not representing action explicitly here. And that's because really there are no actions. All there are small changes in the spatiotemporal characteristics of the objects in our environment. So here I've shown each individual frame as it unfolds. There's just a knife getting closer, and there's a chef bending over, and the onion starts to cleave and separate into distinct pieces. So on this account, we view action as an emergent representation. So representation abstracted across those intersections of object history. So what's the theoretical challenge of trying to represent object tokens? Well, one challenge is, how do we build these representations on the fly? How is it that we each now have a representation of the onion that Gordon Ramsay was chopping in that video? Now there we directly apprehended the onion using our visual senses, but we don't have to use vision in order to build an event representation. I can just use language. I can tell you about my dad's hat. It's one of those Cossack hats that's sort of triangular shaped and a sort of curly, wiry wool. And there's a whole story to this hat that I shall leave to another time. But we each now have some representation of this specific hat. So the question then is, how do we do this? And I'm going to just take a step back and point out that normally when we think about meaning, we attribute meaning on the basis of systematic associations across our experience. This is a standard approach from within the field of semantic memory. What Zach Egfees and I claim is that we generate token representations on the basis of the non-systematic associations across our experience. And I'm just going to illustrate that now with this picture of Gordon Ramsay chopping parsley. And the question will be, how do we generate a token representation on the fly for this parsley? Well, the first thing we do is we apprehend through the senses the green stuff in front of us, and we just associate that with the other stuff in front of us in the environment. So these yellow arrows are meant to represent these random associations. But seeing that green stuff also activates in semantic memory some representation that we have generated across our experience of parsley. And so we activate that representation. And now that becomes an activated, if you like, entity within our representational space. And so that also becomes associated with the other stuff in our concurrent environment. Now, not everything is sort of random association. There are some systematic associations. So, for example, our semantic memory of parsley might tell us that usually parsley occurs in our experience on a chopping block, and there is a chopping block. So we have that association, but it is more systematic. But there are also conjunctive associations which will activate entire schema. These are representations of situations. For example, a representation of a kitchen, what kind of things we find in a kitchen, what kind of other events might occur in a kitchen. So we activate the schema, and this complex representation again is associated with the other things in the environment. So what we see here is that the parsley has a very complex representational signature that makes it unique across time relative to any other parsley that we have encountered in that time. Now, of course, we don't just see individual snapshots, individual photographs of things. We tend to experience events as unfolding through time. And as it unfolds, it's not that we forget the previous moment in time, rather there is an echo. So in this portrayal here, we see that echo. So this actually gives us a very important opportunity. So at each moment in time, we can create these associations between the different objects in our environment. At the next moment in time, we do the same thing, but because we still have that echo from the earlier moment in time, we can now associate things at the current moment with things in the previous moment. And we can do this throughout the unfolding of the event. And we're supposing here a recurrent architecture, that is one where we have access to a fading memory of the past whilst we're experiencing the present. And we're doing that in service of a system, we suppose, that is trying at each moment in time to predict what the world will look like at the next moment in time. I'm going to come back to this when we describe some of the computational work that we've been doing. So this process of sort of randomly associating everything with everything else in the environment is called relational binding. It has a very established history in neuroscience, tracing its origins to Cohen and Eichenbaum's work. It allows one to bind each representation to its context and to bind each representation through time, modulated by things like saliency, attention, and semantic memory. The question, though, is how do we do this when we just experience the language? Well, it's actually a very, very similar kind of thing. We get a very unique signature that distinguishes what I'm talking about now from everything else that you've heard. And it works like this. So let's replace Gordon Ramsay with me. This is me in a crumpled shirt. We'll replace the parsley with some speech that seems to be miraculously coming from my belly button. And when we hear this speech, that activates semantic representations of my father and a Cossack hat. And those representations occur in the context of the environment that I might be in. Ordinarily, it would be a conference hall, but now, of course, it's my spare bedroom. And so we associate the speech with these other elements in the environment, and we associate those representations with those other elements in the environment. So it's very similar to the process of relational binding. It's the exact same process, in fact, as when we directly apprehend an event. So a token is simply a unique trajectory, a unique flight path through state space across time. So just to summarize this a little bit here, object tokens are trajectories through space, as I've just said. They're associated with their past through relational binding across time. And this means that object tokens carry their history with them. They are an entire trajectory. They aren't just a point in time. They're a trajectory through time. And this means that activating a token should reactivate its multiple associated states from the past. And that's what we're going to turn to next when we look at the empirical studies that we've done to explore this. So we'll turn to behavior now. And before we do that, though, it's worth reminding ourselves of just one observation, which is that really representations of, at a minimum, initial and resultant states of an object need to be simultaneously active to comprehend an event. For example, if all we did was represent in our minds a running commentary of The Onion, such that we just represented the onion in its current state at the current moment of thought, we wouldn't know that the onion had been in a prior state. We wouldn't know that an event had happened. We wouldn't know that the onion had changed state. So a priori, representations of initial and resultant states of an object need to be simultaneously active to even comprehend an event. In a sense, we don't need to do experiments to test this. But nonetheless, it's a challenge to do that, so that's what, as an experimental psychologist, I do. So how we test for this coactivation? Well, multiple object states means that there's an ambiguity. That is, that there are multiple representations available, and I have to choose from between them. Okay, so I'm going to just describe two sets of studies. The first study was conducted by Janina Pristauker as part of her doctoral work. And what she did was she gave people sentences such as, "The clown will choose the shiny balloon." There's not very much going on here. She presented this online using Prolific and Guerrilla software. And participants would read such a sentence, and then they would see a picture and have to say whether the object in the picture had been mentioned in the sentence. So it's a sentence picture verification task. And Janina collected the reaction times to respond yes. So this is what the data look like. Although I mentioned that she collected reaction times, I'm going to actually show you the proportion of yes responses. The reaction times mirror these data exactly. And all the differences that you will see are highly significant statistically. So when she gives people "the clown will choose the shiny balloon," on around 87–88% of occasions, participants will say, yes, that object had been mentioned in the sentence. Now notice that it's a deflated balloon, and Janina had done extensive norming to show that the typical representation of a balloon is in fact of an inflated balloon, not a deflated one. It turns out this is actually quite important, and I can come back to that if anybody wants to ask me. So this is going to be a kind of baseline that we're going to use, and now we're going to ask, well, what happens when people read "the clown will inflate the shiny balloon," and they see the same deflated balloon? This is the atypical case. It is not the canonical representation of a balloon that people have when they think of a balloon. But remember that the theory here is that when I comprehend this sentence and I represent the event that it describes, I will create representations of the balloon both in its initial state and in its end state. And so in that case, the representation of the initial deflated state should be more accessible. And what we find is exactly that. We find a significantly greater proportion of yes responses to that deflated balloon relative to the case when participants read "the clown will choose the shiny balloon." Now, the reaction times were the exact converse. They were faster to say yes to the deflated balloon after "the clown will inflate the shiny balloon" than after "the clown will choose the shiny balloon." Now, just as an aside, Janina also included sentences such as "the clown will choose the inflated balloon." And we have the idea here that the morphosyntax of inflated as a prenominal participle is focusing attention on the end state and is essentially an instruction to the system to suppress or block the activation of the initial state of the balloon. And in fact, we see a very considerable suppression effect here in the proportion of yes responses. Okay, so I mentioned that representations of initial and resultant states of an object need to be simultaneously active to comprehend an event. And I'm going to turn now to a different way of establishing the same thing, this time using fMRI. Again, when testing coactivation, we can use the fact that if you represent multiple object states, you have an ambiguity. But now we're going to take account of the fact that ambiguity is often accompanied by conflict. And we're going to use this in a series of fMRI studies to show that multiple object states are accessible and available to the listener or hearer. So how do we do this? Well, our strategy is to find which bits in the brain respond to Stroop conflict. The Stroop task is where you have a word such as yellow, but printed in the color brown. And people have to respond to the color it's printed in rather than to the color that the word names. So if the word yellow is printed in brown, they have to press the brown key in the scanner. So we find which bits in the brain respond to Stroop conflict because we know that these bits light up to other kinds of conflict also. We see, for example, that they light up to syntactic ambiguity and the conflict that that creates. We're going to have people lie in a scanner and read pairs of sentences such as these. The chef will chop the onion, then she will weigh the onion. Or the chef will smell the onion, then she will weigh the onion. Now, critically, the onion that is weighed in the first pair of sentences is a chopped onion. But again, because of norming, we know that when someone smells an onion, they activate a generic representation of onion, which is an intact onion. So we know that in the second sentence, when you hear or read rather, then she'll weigh the onion, that the onion being weighed is probably an intact onion. So in the case of chop the onion, we have these distinct representations. The initial state is intact and the chopped state, and the state that is weighed is chopped. We don't have that those two different states in the case of smelling an onion and weighing an onion. So we're looking for those bits in the brain that respond to Stroop conflict. We have people read these sentences, and then we see if these bits of the brain that respond to Stroop, and only these bits, are sensitive to chopping the onion versus smelling the onion. That is, do we see evidence of conflict when we've read chop the onion compared to when we've read smell the onion? If we do, that implies multiple simultaneous representations of object state. Well, to cut the longer story short, yes, Stroop sensitive voxels in posterior ventrolateral prefrontal cortex, that's essentially LIFG, which, for those of you that aren't neuroscientists, encompasses the region of the brain that has Broca's area, that really all-important language area. So Stroop sensitive voxels in this part of the brain were sensitive to the difference between smell and chop. That is, they were sensitive to object state change. In fact, the bold response, the thing we're measuring in the scanner, correlated with separate ratings provided by separate participants of the degree of change that the objects underwent as a result of the event that was described in that first sentence. So when you chop the onion undergoes more change than when you weigh the onion or smell the onion. Now, we actually did something else. We contrasted the chef will chop the onion, then she'll weigh the onion, with the chef will chop the onion, then she'll weigh another onion. All we've done is change whether it's the same onion or a different onion. We should see representational conflict in the first case, where the weighed onion is, when we activate a representation of onion at that point, we should have available the history of that onion, and that history has both the unchopped and the chopped states, and there'll be some conflict. We have to decide which one we want to choose for the weighing. But in the case of the chef will chop the onion, then she'll weigh another onion. In this case, we instantiate a new onion from semantic memory, a new generic onion, which will not be in that chopped state. So when we weigh another onion, there is no conflict. There is only one state, we presume. So what did we find? Well, we found that effect in posterior ventrolateral prefrontal cortex in the first case. But in the case of another onion, we found no effect. So it appears that to observe this competition, we need to bind into the same token. It has to be the same token that we activate at weigh as had been introduced in the first sentence. These are actually the data across 4 different studies. The brain on the bottom right is actually due to work of my student Zach Ekvies. The brain on the bottom left, work of my student Janina Pristalka. And all the other figures are from my collaboration with Sharon Thompson-Schill, Nick Hindi, and Sarah Solomon. We see far too many of those pictures in the talks and the papers that we read, so I'm not going to go into those in any detail. All I'm going to do is conclude that conflict suggests multiple simultaneous representations of object state. That is, multiple distinct states of the same object are represented when we process these kinds of event descriptions.
I have a question not related to the data. What role language actually plays in state changes of objects, if at all? Or, if I go back and back the theories of modularity that keeps coming to my mind, and the impenetrability issues and so on and so forth. So how can it has nothing to do with the experimental strategies, but a more conceptual.
Right. So that's a really important question. I actually address it at the very, very end of the talk, almost in passing. When I've done variants of this talk before, without the computational work that I'll come to next, I've actually addressed that issue right at the very beginning. So what I'll do is I'll just describe briefly for you now something that I mentioned, at the end, which is that when we directly observe an event, we can directly observe the dynamics of that event. We can observe the participants, we can observe their temporal contingencies and contiguities, the temporal relationships between them, the temporal relationships between the change in one, the change in the other. And so we can directly apprehend the dynamic of the event. When we get language has to do a number of things. It has to tell us what or who participated in the event, and we have to use our knowledge of the language to retrieve the relationships between those participants in the event, and to retrieve the dynamic. And so one way of thinking about it is that language, the function of language, is to instantiate the dynamic that we don't have access to through not being able to apprehend the event directly. So its function is really critical, and it's more than, I used to believe, and I find it interesting how my own way of thinking about things has changed over, sadly I can now say, over the decades. I wish I wasn't that old. But I used to think that language is just the same as observing an event. It's just a proxy for an event. But it has to do this different thing, and it has to do it in a different way. So I can observe an event directly. I can see the dynamic. I don't need past experience to see the dynamic. I may need past experience to understand it and to understand the consequences and what may happen next. But I can see that those temporal relationships unfold in real time. With language, I have to go to semantic memory to retrieve the information that will allow me to instantiate that dynamic. And so there's a very different interplay between the memory systems, and in fact, there'll be a very different dynamic, most likely instantiated by the language. So the function, you know, it has a vital function in respect of event representation.
One more question, Gerry, if you can take it. We have had a lot of discussions all over the journals on prediction, and a lot of people are interested in prediction. I too have done a couple of things. Now, state changes of objects in the visual domain have their own predictions. I mean, because of my usual habits with them, I can predict what's coming next, how it would look like, and those perceptual sensory motor expectations. And language too has a predictive mechanism built in it. How do they come together when you pass them together? Of course, it's a very interesting interactive issue, but I want a very simple answer for the audience.
Okay. So the way I think about it is that there's a common representational substrate. So when I see someone chopping an onion, how do I know it's an onion? How do I know why the chopping is happening? That's because I'm retrieving information from semantic memory. The same information I retrieve from when somebody refers to an onion in language or refers to the action of chopping. And so you're retrieving the same representation. So these representations exist in the same substrate, I think of it as, regardless of whether you're directly observing the event or using language. And the same semantic memory structures that allow you to anticipate, given your experience, what may come next, operate in both domains in exactly the same way. I think that's the critical thing. So, you know, it's interesting. I came to that that understanding, if you like, a long time before I came to understanding the content of event representation and this relationship between language and vision in respect of instantiating the dynamic.
Okay. All right, I think we could move on.
Okay, good. Before we move on, I just want to mention a little aside. This is really for Andriy Miachikov and others that know Andriy. In fact, Andriy will have recognized that when I put up that animation where I replaced Gordon Ramsay with myself in a crumpled shirt, the background that popped up was actually the lecture theatre in which the AMLAP conference a year ago took place, almost exactly a year ago. It was in November, but was it beginning of November or October? I can't remember. Anyhow, it was effectively a year ago, and at that meeting, sorry, Andrew, you were saying? No, it didn't come through. So at that meeting, one of my collaborators, a new collaborator, he came up to me. I'd never met him before. It was Forrest Davis, and he introduced himself, and he said, hey, I've got a recurrent neural network that implements your PhD work, your doctoral work. I did that doctoral work before this guy was born. And I was deeply suspicious. I thought there's no way that a recurrent neural network could do the kind of thing that I had been working on, which was essentially contextual influences on syntactic ambiguity. And so I thought, well, okay, I'll humor the guy. You know, we've got the conference dinner. You know, I'll go with him. We'll chat. The guy blew my mind, and exactly a year, almost to the day, certainly to the week, a year later, Forrest and I submitted our first publication, in fact, to the journal Cognition. We've been invited to revise, so it's not been rejected, and that's great. And in fact, there were no issues. The paper rambled on too long. That was the main objection. So I've got to cut it down. I tend to ramble on too much. So within a year of AMLAP, we managed to get the first outputs from that collaboration, that new collaboration, that is absolutely due to the wonderful AMLAP in Moscow. And the work that I'm going to talk about next is exactly that collaboration. I'm not describing everything that's in the paper, all the simulations, just a couple of the main ones. So I'll move to that now. So Andrea, I have to thank you for AMLAP. It had a very big effect on my life.
Oh, totally, it was totally my pleasure.
I'll start this section on computational modeling by explaining why we chose recurrent networks for this work. I've mentioned earlier that events unfold across time. They're not like photographs that are just a single moment or depict just a single moment. Rather, they are a succession of moments, and at each one of these moments, there is a trace or an echo of the previous moment. So I've tried to illustrate that with this cartoon. Now, events are all about things that need to be tracked over time. And to track something over time, you need that trace, you need that memory of prior time. And recurrent neural networks are particularly good at encoding that kind of memory. That's what they're for. So recurrent neural networks encode their inputs as trajectories through time, exactly the kind of encoding that I mentioned at the beginning when talking about the theory that underpins our work. Now, I don't expect you to know anything about how recurrent neural networks work. Many of you will do, but for the remainder of this section, you don't need to know. You just need to know that they are particularly good at encoding variation across time. So let me tell you, before I tell you what we did, let me tell you about the models that we used, the computational models. These were recurrent neural networks with LSTMs. These are long, short-term memories. They simply keep those echoes alive as long as they're needed. Each network had a vocabulary of 50,000 items, and we trained two sets of networks. One set were trained on Wikipedia, a subset of Wikipedia with roughly 103 million words. Another set of networks were trained on 100 million words from elsewhere on the web, excluding Wikipedia. In fact, they were taken from Reddit entries and the links out onto the internet from Reddit, but again, excluding Wikipedia. Now, for each set of networks, whether Wikipedia or the web, we had 25 different networks, each with a different random weight initialization. So we're going to treat each network a little bit like an individual participant who had very slightly different experience. And the task of the networks was to go through each corpus and take in one word and predict what the next word would be. So this is the standard prediction task that Gerry Altmann introduced to us all. Okay, so I'm going to describe two things that we did, just as an example of the work we do. And one of them was encoding degree of change. I'd mentioned earlier on that when we put people in the scanner, they can read sentences like the chef will chop the onion or the chef will peel the onion. And human participants will rate the change that the onion undergoes in the chef will chop the onion as greater than the change that the onion undergoes in the chef will peel the onion. And these ratings correlate with the bold response. So the rating they give for a sentence with a verb like chop will be higher than the rating that they give for a sentence with a verb like peel. The question that we wanted to know is whether our networks would provide equivalent information, even though, of course, they weren't trained to do this. They were just trained on that prediction task. So could a recurrent neural network know that peeling the onion isn't as big a change as chopping the onion? So how do we do this? So let me just start with a kind of graphical portrayal of what we do. So let's suppose that we have some representation of an onion, and then something happened to that onion and we get a new representation. Let's say it's chopped onion. We can compare those two representations and ask what is the difference between them. We might count the difference in the pixels, or we might look at the activation pattern in the neural network. Similarly, we might have an onion, but now we have a peeled onion that we are comparing against this. And again, we can ask what is the difference, what is the delta between these two representations. And these representations may be, again, a pattern of activation across the network. In fact, when we look at the networks, what we're doing is we're looking at the patterns of activation across the hidden layers. Our networks had 2 hidden layers. We were looking at the topmost of those hidden layers. So what do we actually do? Well, we are going to give the networks these sentences to read. And instead of showing them onions, what we do is we ask, what is the representation we get if we simply give the network the phrase an onion? And we're going to look at that representation. It's a pattern of activation across that hidden layer. Actually, it's a very, very large vector. And we're going to compare that pattern of activation to the one that we get at the offset of the sentence. So after the chef will chop the onion, if the network knows about what happens to onions when you chop them or when you peel them, the difference in the representation that we get at the end of the sentence compared to that first representation that's due to an onion, that difference should be greater for the chop sentence than for the peel sentence, because the representation of an onion after it's been chopped should be more different from a generic onion than the representation we get after the onion has been peeled, again compared to that generic onion. So we had a number of sentence pairs. I've put the information at the bottom of the slide here, and in fact we found that the network estimates calculated this way, comparing these 2 activation patterns, in fact we use simply Pearson's R to compare the 2 vectors. The metric we get from the network correlates with the human estimates. It's not a huge effect, it's a correlation of 0.2, but it's significant. And it didn't matter whether we used the 25 networks trained on Wikipedia or the 25 networks trained elsewhere on the web. So the bigger the difference for the networks, the bigger the difference for the humans. Of course, 0.2 is a very small correlation. We're only accounting for a very small proportion of the variance. But it's worth remembering that the networks only have experience of the language, whereas the human participants, when judging the degree of change that an object undergoes, can use not just their experience of a language, but their experience of the world as they have directly viewed it. So it's not surprising that the proportion of the variance that we can explain through the model is so low. Okay, and now I want to move to a second thing that we did, but using the same sort of technique, but to ask a more, in some sense, novel question. I'm going to change the example to ask how are representations maintained as sentences unfold. So we're going to move away from onions, I'm afraid, and we're going to talk about farmers. The farmer will shear the sheep, then he will feed the sheep. Just to help you, here is our farmer. There is a reason for this graphic, as you'll see in just a moment. So what we're interested in here is how does the network propagate forwards the representation of the agent of the events, the shearing event and the feeding event. How does the representation of the farmer propagate through the first sentence and into the second and possibly beyond? So we need it to propagate forward because we need to establish the dependency between the sheep and the farmer. They are engaged in that event. It is their histories that intersects. And then, of course, at he, we need to pick out from the mess of representation that is activated within that hidden space. We need to retrieve the representation of the farmer. And then again, there is dependency between the farmer and the sheep at the end of the second sentence over here. So how are we going to look at this propagation of the agent of the event? Well, we're going to do something very similar to what we did before. We're going to look at what is the internal representation after simply reading the farmer. And then at each subsequent point in the sentence, we're going to compare the activation pattern at that hidden layer at that point to the activation pattern we had got simply after the farmer. And we can do this at each point in the sentence. Now, what we actually did is we added a third sentence. So we had the farmer will shear the sheep, then he will feed the sheep, then he will think about the sheep. We just wanted to really stretch the networks to see what they could do. And what I'm going to plot in this graph is the similarity in the representation at each moment in the sentence, at each point in the sentence, relative to the farmer, the activation pattern we get just in response to that noun phrase. And it should go up and down. And that's what we see. There are some notable things here. So, for example, we have these two high peaks at he. That looks very good. We would like that. And we have some slightly lower peaks at each of the mentions of the sheep. And remember, there is that dependency between the farmer and the sheep in each of the sentences. Now, this all looks very good, but we can't be sure that these patterns really reflect what we think they might reflect. But in some sense, that doesn't matter, because what I want to do is address a very, very slightly different issue, which is not why do we get these patterns in the network, but rather what patterns would we observe if we did the exact same thing, but in a scanner or an MEG or a high-density EEG system, asking the same question about how do representations propagate through these sentences. We don't know the answer to that. To our knowledge, no one has asked that question. And it may actually be a really important question to know the answer to, because there are some, we have some predictions that we might make about when we may expect to see peaks and when we may not. So there are really two questions. One of them is, do we see, or can we see, this kind of waxing and waning if we do a representational similarity analysis in the way that we've done here, but with humans? And then the other question is whether the pattern of waxing and waning that we see in the networks might predict the waxing and waning that we see in the human case. Given what we know about semantic memory, we certainly expect some of the network's patterns to replicate in the human case. Now, we haven't done this work yet, but I'm presenting this here really as a way of showing how there can be a very strong relationship between computational modeling on the one hand and exploring equivalent questions, but empirically, neuroscientifically in the human brain. There's a kind of synergy between those two fields. There's a challenge that I want to introduce now as we come towards the end of this section on computational modeling that I think nonetheless is rather important, and it does complicate things. So we wanted to know whether recurrent neural networks encode discourse entities or discourse objects as trajectories through time. It does seem that representations are propagated forwards through and between sentences. Now, I put representations in scare quotes because we can think of representations within a dynamical system as really just constraints on where that dynamical system can move next. Okay. As these representations propagate, they change to reflect the events described by each sentence. We saw that with the chop the onion case. And as they propagate, they wax and wane as a function of the past, present, and future input, the input that we're predicting. Turns out they also wax and wane as a function of the impact that these inputs have on the system. So although I didn't talk about it here, we find that certain things will perturb the system more than other things that will perturb it less, and that has an impact on the waxing and waning. But the question is, are these networks propagating representations of tokens, individuated entities that have continuity across time? Well, we're actually no more able to determine the answer for networks than we are to determine it for humans. We assume that we encode objects as tokens. Here is my iPhone, and you are now encoding this as an object. I take it away, I bring it back, the question is this: are you encoding this now as the same object with a commitment that the two things are the same? Or is it simply the case that when you see it again, it is the most similar thing to your memory of that other thing that you had just seen a moment before I had moved it away? It could be that you encode these two things as being highly similar without a commitment to them actually being the same. We don't have an empirical method yet for distinguishing those two cases. In one case, there's an identity relationship encoded. In the other case, there isn't. It's just a similarity relationship. So we can't tell whether people are encoding tokens. We have an intuition that they are, but as you know, as psychologists, we cannot simply go by intuition. So we don't want to hold the network to a higher standard than we hold people to, and vice versa. Okay, so just to summarize the computational section, computational models offer insights into, in fact, the gaps in our knowledge. For example, we can't measure tokens in the human brain, just as we can't in artificial ones. It's tempting to think that because we have access to that pattern of activation, that we can make sense of it. It turns out we can't, except by doing behavioral studies, that is, asking what is the behavior of the network. There are some ways of doing that, using clustering techniques and so on, but still, at the end of the day, you have to ground the clustering in behavior. Computational models also offer insights into new ways to interrogate the human mind and explore properties of its representational content. So that was the idea of looking at that waxing and waning of representations as they propagate through the sentence. Okay, to summarize the whole talk, and if there really is only one slide that you take away with you, this should be the one. So this is really the key issue now. And really it's simply this, that events are simply cases when states change and optionally when trajectories collide. You can have state change when there aren't multiple trajectories. A single object can change by itself. When you have multiple objects, those correspond to events with multiple participants. Event comprehension consists in the encoding, updating, and retrieval of intersecting object histories. That is, trajectories of token states and changes in state that extend from the past into the future. So event representations are simply a part of the dynamical representation of tokens and their trajectories through feature space, physical space, and time. In a sense, event representations and token representations are the same thing. And language comprehension consists in the instantiation of dynamical representations of object histories. So when we observed that video of the chef chopping the onion, we could directly apprehend the event dynamics. But we can't do that when we just use language. So we have to use that language based on experience during the acquisition of the language. We have to use that language to instantiate the dynamics of the event. Okay, so with that, I shall thank you for watching, and I'll be happy to take questions. Okay, we're back again, but that was it. There's no more, I'm afraid.
That I've been thinking about the last slide about the real question, how dynamically things are represented, because there's a speed issue. Like visual perception is pretty fast, and people say it's unconscious. I mean, we only arrive at the final leveling. What is it at the end? But it's pretty unconscious, and I'm sure that you're well aware of developments in visual cognition. And language, we're not yet sure how fast, although there are some speculations that, processing a sentence takes this kind of time. Now, when it comes to the multimodal interaction, how the speed issue is solved, both as a neural problem or maybe as a behavioral problem if you're expecting a response.
So I think that's a really interesting question. So I want to I want to start by saying something very controversial. Many of us got into psycholinguistics because we thought that language is special. It sets us apart in certain well-known ways from other species and so on. But I've come to think of language as really being no more special, and this is the controversial thing, but it's very liberating to say it. To think of language as no more special than the cables that go along my street that deliver internet, TV, whatever it is. It's the encoding at the other end of the cable or at this end of the cable that is what matters. But there's this interesting puzzle, which is that the transmission of the signal along that cable will have its own dynamic. Language has its own dynamic, and that is different from the dynamic that we see when we directly apprehend events. But that question is no different from how do we match the dynamic of human thought to the dynamic of human events. So we can think of the last time that you flew from Europe to India, and it took, let's say, 8 hours or 10 hours or 12 hours. I have, you know, I'm sorry, my ignorance, I have no idea how long it takes.
About 10 hours.
About 10 hours. But as we think of that, of course, we do not require that thought to unfold over the 10 hours that it took. In that sense, when people talk about cognition as simulation or language as simulation, we're not simulating the temporal dynamic of the real world. So you have the same issue with respect to thought, which is that it has a different temporal dynamic from the things that you are thinking about. Language has a different temporal dynamic from the things that you are communicating about. And I think that the reason that you can match the two is in fact due to a property of dynamical systems, which is that at any one moment in time, I mentioned earlier about representation as being really a constraint on where the system can move. What, you know, if you think of it as a physical system that's changing shape across time, representations are constraints on what shape it can become given the current shape. The human body has exactly that constraint. When I'm walking, for example, or I'm reaching, where I can move my arm to next is determined by where the arm was before, and to an extent the trajectory that I have taken in that movement. And within the context of that notion of representation and these constraints, because the constraint on when you can go next is a product of where you've come from, that trajectory, a little bit like throwing a stone through the air or a pendulum swinging, any one moment in time, any one snapshot of the dynamical system is actually capturing that trajectory through time. It's the temporal equivalent of a holographic plate, where when you break the plate, every piece of glass has, at a lower resolution, the complete image. Every moment in time has, at a lower resolution, the complete trajectory. And because of that, as long as it's a dynamical system, I can map those individual moments that are trajectories onto moments that are trajectories from out there. And I think that's part of the secret. Now, of course, there's a lot of modeling that one would need to do to show that, but I think that that's likely one part of the solution to the puzzle of how it is that we can not just do the easy stuff, which is say, well, if my language mentions, 3 participants and I see 3 things interacting out in the world, I'll put them together. That bit's easy. One can do statistical operations that will put those together. And in fact, I've built neural networks that do that. Far more complex is that issue of, well, when the dynamic's different, how do you do that? The dynamic of the language versus the dynamic out there in the world. And I think that the key there is that, in fact, there is no outside. It's all encoded in this same dynamical system. That is, we've taken that dynamic and put it into this single system where either language can reinstantiate those moments that are trajectories, or my other senses can instantiate those dynamics. That was a very long-winded response, but it's long-winded in part because I think it's a really interesting question that has been actually overlooked. I think people haven't really asked that question at all, and it's a very important question.
Yeah, because when I reflect back, let's say I pick one most in the second of Landau's work with transduction, language does to visual scenes, and they seem to think the language cannot do because of its own inherent inability. And I truly believe that language, structurally speaking, let's say a dynamic visual scene is unfolding, and I want to momentarily talk about it. It's very impossible. I have to wait and watch what words and what nouns and what verbs. So there are limitations. But then language is primarily for a communicative purpose. I need to extract things that either make sense to me or to somebody else. So I have, back of my mind, I'm doing that. Language is just not momentarily, dynamically capturing verbally with verbal signs exactly what my perceptual system is, getting me.
Right. Right.
So it remains a very challenging problem to crack with the new neurosciences but I'm quite sure that maybe some breakthroughs.
Well, I think that, time and dynamics is something that actually is rarely studied. I mean, people study how we represent encyclopedic time, but there aren't many people that really study the cognition of time. There is a point here. I was wondering if changes in mental states would be treated similarly, so making someone happy. And in fact, I think exactly so. So if I learn some fact about Ramesh that changes my the knowledge about him, that is a change in state in exactly the same way as representationally as chopping the onion is a change in state. So in some sense, this, although I focus very much on object state change as being really key, object state change is really just the accrual of information. And so it's really just a comparison between how much information I have now and how much information I had a moment ago. So I think that, if I'm lucky and this work doesn't sort of die a death and people, carry it forward, there will be a time when we take an information theoretic approach to this rather than a sort of object state, very cognitive representational approach. So, I think that this is really about accrual of information. I think that it doesn't have to be changes in physical state. It could be changes in value, in affective state, in ownership, in just knowledge about that onion is the onion that Ramesh bought, as distinct from the ones that I bought. Though that accumulation of knowledge constitutes change, and I think it will have exactly the same impact on the representational system. So what this means is that when somebody tells me that Ramesh is happy today, and I refer back to Ramesh in my mind, I will activate that not only is he happy, but that there was a moment when presumably he was not and he was sad. Those will become simultaneously active, just like the distinct states of the onion.
Yeah, any other questions or comments by anyone? Please go ahead. We will have to watch time. I think we already. Then on my last question, and I tend to ask this question, depending on the fields that it present, where is psycholinguistics moving as for COVID, post-COVID, and there are many things to ask here. Where do you see it going next 10 years?
So I think where it has been going, I'm sort of mindful of the fact that you're recording this, so people, you know, I don't have the luxury of being able to say something that will then be lost forever, and it doesn't really matter what I say. But I think just to go back to that last point I made about information theoretic approaches to language, I think there's been a lot of work on that. People have been doing an awful lot of work on surprisal. And I don't think that's necessarily the way that in 10 or 15 years' time, looking back, we will think was as productive as we hoped. And the reason simply is that, well, okay, so I'm surprised. That doesn't tell me about the content of what I have built. Now, in some sense, people who calculate surprisal will say, well, it does because surprisal is reflecting a difference in the content, for example, that you anticipated and the content that you got. You know, so that's sort of one way of thinking about one of the things that surprisal can tell you. But it's just telling you how close it is. It's a little bit like a similarity space in semantic memory simply tells you that some things are similar to other things, but it doesn't tell you what the representational content is. And that's the question that I'm interested in. So in the field of event cognition, there's absolutely seminal work done by, for example, Jeff Sachs and his colleagues on event segmentation. How do you, how is it that we perceive discontinuity in that stream of information that we receive about the unfolding world or the unfolding language? But those discontinuities and segmenting the event doesn't tell you about the content that is in there. It doesn't tell you what of the external world has been encoded in your internal encoding of that event. I think that that's going to change. I think that, you know, I'd hope that the work that I and my team have been doing will push things a little bit in that direction. I think it may open up the field a little bit. There are a few people who are working on object state change now. So that's where I hope it will go, of course. But I think more broadly, I think people are slowly going to come to understand what both the opportunities that information theory offers and what the limitations are of information theoretic approaches. And, you know, the way that I put it into, you know, the contemporary world rather than Shannon's world, you know, back in the last century, is that I can measure the amount of information that is going through the cable into the back of my computer or over the internet into my computer to my browser. But the browser is doing the rendering. The browser is the thing that knows how to interpret the equivalent of the markdown language, the HTML, to render it, to render the text, to render the graphics. So I think that some of psycholinguistics has been studying the rate of information coming in through that cable, rather than studying what is the process by which we decode that, or in production encode that. And, you know, when Shannon first talked about information theory, that was a given, that you have the encoding and the decoding, and then there is this channel. But that channel is the transmission of information, and you can measure the transmission and maybe the optimal transmission of information. You can talk about things like signal and noise, but those things do not tell you about the encoding and the decoding. They don't tell you about what knowledge do you have to have accumulated through your experience to be able to do that. And I think that over the next 10, 15 years, we're going to see a shift more towards those sorts of questions. That may be a hope on my part, but I think it's beginning to happen.
All right, I could go on, but I think it has been pretty exciting, and if there are no other questions, maybe they would come and contact you after they see the video. Many people.
Yeah, I'm super happy for people to email me. I'm happy to answer questions by email about the talk or about anything.
So that would be great, and I must thank you for a pretty theoretically rich talk and a very exciting animation. And
thank you.
It's very interesting, actually. I mean, I often thought I'm not capable of making those kind of dynamic cartoons. They're really helpful in, getting the points free. So I think it has been a fantastic evening talking to you, Gerry, and maybe.
Well, it was a privilege, a real privilege to be here, and just thank you for giving me this opportunity.
And when the usual things go better, we might see one another somewhere.
I really sincerely hope so. And I have one positive and one negative thing to say about the pandemic beyond the usual. The negative thing is I would love to be there in person rather than doing this over Zoom.
To telling you, Andrew was there. We have a big grant where we were about to do a great meeting in Goa in February.
Right.
And then, we would be happy to come back to one of these nights, and you would be certainly there with us.
I would love that, but one of the positive things to come from the pandemic, every cloud has a silver lining, is that the ease now with which we use Zoom and other online methods for communicating has just opened up the world. So when I look at the caliber of the people, excluding me, who've been on this series of talks, I'm sure a part of that has been because it's just easier now for us to literally cross continents from our spare rooms. And, I really hope that after the pandemic, we will remember this lesson that we can open up the world even more than air travel did. And as academics and scientists, we need to continue this trend that has allowed science just to become more accessible to more parts of the really incredibly important community that we are all a part of.
Yes. Yeah, I don't feel the same way, because kind of people that were, graceful enough to accept just because it was easy. Not that, flying to India, though we had opportunity to do stuff, and we will get back to that mode, but I think we should continue with this as well. And
yeah, I intend to try and introduce an online series at UConn where, maybe it's only a few times a year, because it's always very nice to meet people in person. But it does mean that now we can actually go to Europe. We can come to India or to China and or Russia and bring people now to us through Zoom to present their science in ways that we just couldn't before. So, I think this is a real positive, and I think that this series of talks that you've arranged is exactly the kind of living example and embodiment of that potential. So, both congratulations for doing this, and thank you for showing us how to do it.
It came out of boredom when it all began, and I was in my hometown in Orissa in March or April, and I was thinking what to do now. So it emerged from there, and then it has taken a form now. And thank you for motivating and for your good words. And we will continue with more in coming times. So I think we will have to, kind of close the session. And
Ramesh, thank you again. I'll send you an email with links to the actual videos so that you can have those as well.
And I thank all the students and the audience who have been with us. And please do join us for another episode with somebody of eminence. Thanks a lot, everyone.
Okay, bye everyone.